fraction of seconds we'll be live completely.
Okay. No issue. Okay.
Yes,
So,
ma'am, we are live.
okay. So, I welcome the second speaker of the day, Professor Patrick Dasgupta, who is well known to all of us by now. So, I welcome you, sir, to this program on learning physics with conceptual and problem-based approach, organized by National Academy of Sciences India, Delhi chapter. It's a 10-week course which started on 27 July 2020. So, kindly share Professor Patrick's intro slide.
Thank you very much, Dr. Bindal. It's a pleasure to
The
join
pleasure
this.
is all ours. So I would like to introduce you to the participants. So Professor Patrick Dasgupta is a professor in Department of Physics and Astrophysics, University of Delhi. After receiving the National Science Talent Search Scholarship in 1976, Patrick Dasgupta joined BITS Pilani to do a 5 years integrated MSc Physics. In 1981, he took admission to PhD program at IISc Bangalore, but left for TIFR Mumbai in 1982 as a research scholar in theoretical astrophysics group. In TIFR, he did his PhD with Professor Jayant on luminosity functions of radio galaxies. During that period, he also collaborated with the late Professor Woodbridge, USA, to work on quasars and galaxies. Soon after submitting his PhD thesis in 1988, he joined IUCAA Pune as a postdoctoral fellow. During 1989-90, he had short stints at the University of Wales, UK, as a senior research fellow to learn about gravitational waves data analysis techniques, as well as the Observatoire de Paris, to have an exposure to the topic of gravitational radiation from pulsar pulsar. During these visits, he worked with Professor Schultz and Professor Damu, respectively. After his return, he published a paper in 1992-93 with Professor Narlikar on gravitational waves from mini creation events in cosmology. His current research interests include studies related to confirmation of Hawking area theorem from the observed gravitational waves from binary black holes, proposing a unified model for gamma ray bursts and fast radio bursts, modeling dark energy, torsion, and Chern-Simons gravity using a dynamical four-form mechanisms to generate supermassive black holes from Bose-Einstein condensation of bosonic dark matter and
अभी मेरे को सुनाई नहीं दे रहा, मैं 5-10 मिनट में बात करती हूँ.
Savita, you are audible, please be on mute. Of bosonic dark matter and baryogenesis from primordial black holes. He joined the Department of Physics and Astrophysics, University of Delhi in 1993 and has been a full professor since 2004. He has also been active in training and leading students for the International Physics Olympiad under the aegis of Homi Bhabha Center for Science Education, TIFR Mumbai. So, sir, you're most welcome to share your expertise once again with the students. I'm sure they've been enjoying your lectures and they will enjoy further. So, kindly illuminate them with your knowledge. Thank you so much.
Thank you very much, Dr. Bindal, for the kind introduction. All right. So, if my slides can be shared.
Yes. Dr. Savita, please start sharing his slides.
And please go to page number 25.
Can you see the slides, sir?
That's right. I can see it.
Maybe you can make it slightly bigger if possible. Yes. Much better.
Yeah.
So,
and you can go to slide number 25.
25.
The last portion. Yeah. You can go to the last portion. Yeah. This fine. Yeah.
Savita,
so yesterday.
Please take care as he requests you. Please change the slides. Okay.
Okay, sir. Okay, yes, ma'am.
Thank you, Dr. Savi. Okay. So yesterday, in my lecture, I introduced linear operators, which are mapping from, say, vector space V to another linear vector space W. One of the things I forgot to mention yesterday is because of the property 2 that the linear vector space satisfies, namely the operator A, if it acts on a scalar multiple alpha times the vector psi, then the property states that this must be equal to the scalar multiple alpha times the linear operator acting on the vector psi. So obviously this means if alpha is 0, then alpha into ket psi is the 0 vector of the vector space V. While if alpha is 0, the right side equation says 0 into A into ket psi. The operator A acting on ket psi is a vector in the linear vector space W. So therefore 0 into that vector will be the 0 vector in the linear vector space W. So in other words, this relation is very crucial, which says that a linear vector acting on 0 vector of vector space V must be equal to 0 vector of vector space W. So from this, you can understand that certain transformations which might appear to you as linear operators are actually not linear operators. For example, translation. Imagine that you're taking Cartesian coordinates x, y, z in 3 dimension, and you do a translation, let's say in the x direction. That means what? Your new coordinates are x prime equal to x plus some constant a, y prime is y, z prime is z. Such a transformation is not a linear transformation because you can see 0 does not get mapped to 0. All right. The other thing is that from some point onwards, we will only consider linear operators that map the linear vector space V to linear vector space V. Although the general linear operators can map any vector space to any other vector space, but for the sake of the quantum mechanics relevance, we will focus on those linear operators which map linear vector space V to linear vector space V. Can we go to the next slide, please? That's right. Yesterday, we have already covered these examples. Let's scroll down further. In particular, I must once again emphasize that yesterday I argued that ket phi times bra chi is also a linear operator. Right. Now, today we will start discussing about eigenvalues and eigenvectors. All right. As I said, from now on, we will restrict ourselves to those linear operators which map linear vector space V to itself. Of course, all this discussion can be generalized, but for the simplicity, we will now focus on those linear operators which map a linear vector space V to itself. Now, the idea of eigenvalues and eigenvectors stem from the question that are there some vectors for a given linear operator, when the linear operator acts on that vector, the vector's direction does not change. All right. So such questions immediately raise that can we solve the following equation? Supposing we consider a linear operator T defined on the vector space V and ask, is there a solution, the linear operator acting on some ket psi lambda, and you get the scalar number lambda multiplied by the vector ket psi lambda. The reason I have put a subscript lambda is to highlight the fact that it's a special vector which is associated with a particular scalar number lambda multiplying ket psi lambda. So if you have a linear operator T, and if you find that there exists a ket psi lambda such that when the linear operator acts on ket psi lambda, what you get is a complex number lambda times ket psi lambda. Okay, let's go to the next slide. Thank you. So if this solution, if this equation has a non-trivial solution, what do I mean by non-trivial solution? That ket psi lambda must not be the zero vector. So while the lambda can be zero, but the ket psi lambda itself should not turn out to be only the zero vector. I'll tell you why this is the restriction we put on the idea of eigenvectors and eigenvalue. So if you indeed, for the linear operator T, you can find a non-zero ket psi lambda such that the linear operator T acting on ket psi lambda is equal to complex number lambda into ket psi lambda, then this complex number lambda is called the eigenvalue of the linear operator T corresponding to the eigenvector ket psi lambda. All right. And as I mentioned, the reason why you do not include any zero vector to be eigenvector is, after all, we know, just now I showed that any linear operator acting on zero vector is a zero vector. This is trivially true. So therefore, it doesn't require a special class of vectors to be eigenvectors. After all, a zero vector is trivially annihilated by any linear operator. That's the reason why when we discuss eigenvalues and eigenvectors, the zero vector is never considered as eigenvector. So this is very important because we will do some proofs shortly where this idea will be used. That what is the idea? That the eigenvectors can never be zero vector. Right. Of course, in general, the eigenvalue lambda is a complex number because we are talking about linear operators which are mapping from vector space V to itself, and the vector space itself is defined over the field of complex numbers, and hence it is obvious that the eigenvalues in general will be complex numbers. So let's take some examples. So consider the differential operator d by dx, the derivative operator, okay? And this acts on a class of functions. And we know that functions, you can suitably define a linear vector space made up of functions, which are smooth functions. Smooth functions means they are continuous as well as differentiable. Then the differential operator d by dx is obvious, is a linear operator. After all, d by dx of a1 f1 plus a2 f2, where a1 and a2 are numbers, is nothing but a1 d by dx of f1 plus a2 d by dx of f2. Now we are asking the following question. Does d by dx, does it have eigenvalues and eigenvectors? So let's solve the equation. So to determine eigenvalues and eigenfunction, let's look at the equation. D by dx of f of lambda is equal to lambda f of lambda, where lambda is the eigenvalue corresponding to f of lambda. This is a trivial differential equation, and you can solve it very easily. Just divide by f of lambda both sides, take dx to the other side, and integrate. And you will find log f of lambda is equal to lambda x and so on. And you can find that f of lambda x, therefore, is nothing but an arbitrary constant into e raised to lambda x. So what does it tell you? It tells you that indeed, for any lambda, you can find an eigenvector f of lambda x, which is equal to a into e raised to lambda x. But wait a minute. We know that if lambda, which is in general a complex number, if it indeed has a real part, then either for x going to infinity or x going to minus infinity. By the way, there is a mistake here. So x going to infinity or x going to minus infinity. There is a typographical error here. The arrow has got reversed. That is not the idea. Either x going to infinity or x going to minus infinity. E raised to power lambda x blows up if lambda has a non-zero real part. Hence, in order that e raised to power lambda x is a valid eigenfunction, by valid I mean that it doesn't blow up in the asymptotic region, lambda must be pure imaginary. All right. So this is an example to state that how the operator d by dx has a valid eigenfunction, valid meaning which doesn't blow up either at x tends to infinity or x tends to minus infinity. But then the eigenvalue must be pure imaginary. It must be of the form square root of -1 into a constant, any constant a. However, there is a class, a large class. We can go to scroll down a little bit. Yeah, there is a large class of linear operators which have eigenvalues that are purely real eigenvalues. All right. And why such linear operators are of interest to physicists? The reason is that we know in physics, whenever we do a measurement in a lab, let's scroll down a bit. Whenever we make a measurement, we know that uh, the the values, I think we have scrolled down further, but yeah, the last paragraph, that's so whenever we make measurement, we know that the outcome of a measurement is always a real number. Whether we measure the mass of a particle, or we measure the charge of a particle, current of the particle, angular momentum of the particle, these are nothing but list of real numbers. Therefore, it will be of interest to look at those linear operators whose eigenvalues are real. So now we can scroll down because we want to know about such linear operators. Correct. Thank you very much. So first we define something called adjoint of an operator. All right. So consider any linear operator A, which is a mapping from the vector space V to itself. Obviously, our linear vector space is assumed to have an inner product defined. So consider the following equation. Take an operator A dagger. We are already asking about the adjoint of an operator A. So consider a new operator, call it A dagger, and suppose the following equation holds good for any pair of vectors in the linear vector space. That is, what is the equation? The equation number 9. So we are demanding that A dagger be such that for any ket psi and ket chi belonging to the vector space, the following equation is true. Namely, A dagger acting on ket psi, inner product with ket chi, is nothing but inner product of ket psi with the linear operator A acting on ket chi. Okay, and this should happen for any pair of vectors belonging to the vector space V. If such a thing happens, then A dagger is called the adjoint of the operator A. So this is the definition of adjoint of an operator. I will ask all the students to do an exercise. Given this definition of adjoint of an operator, named the equation number 9, please prove that this object A dagger is also a linear operator. A, of course, we have assumed it to be linear operator, and we are saying A dagger is such that it satisfies equation 9 for any pair of vectors in the vector space V. But how do you know that A dagger is a linear operator? But you can prove that if equation 9 is true for any pair of vectors ket psi and ket chi, you can prove that A dagger is actually a linear operator. All right. Now, let us write down all these in the Dirac notation. Remember, in Dirac notation, what is the inner product of ket psi comma ket chi? It is nothing but bra psi ket chi. So that is something we discussed yesterday. So now let us take a look at equation number 9 in terms of the Dirac bra and ket notation. So let's start with equation left hand side of equation 9, which is inner product of A dagger ket psi with ket chi. We know the first property of inner product shows that if we interchange the right and left entries, now we are looking at equation 10. Yeah. If you interchange right and left entries, the inner product picks up a complex conjugation. So therefore, the inner product of A dagger ket psi comma ket chi is nothing but complex conjugate of inner product of ket chi with A dagger ket psi. But inner product of ket chi with A dagger ket psi is nothing but bra chi A dagger acting on ket psi. So therefore, what we have got, the result we have got is inner product of A dagger ket psi comma ket chi is nothing but complex conjugate of bra chi A dagger ket psi. This is the equation 10. I hope everyone has got how we have arrived starting from the left hand side of equation number 9, how we have shown that right hand side of equation number 10 is indeed true. Okay. Now, let us look closely at the right hand side of equation 10. Bra chi A dagger ket psi complex conjugate. Again, let's go back to the original definition of that joint, that is equation 9. This is nothing but inner product of ket psi with A acting on ket chi, which is the right hand side of equation 9. So because in equation 10 we have already proved that inner product of A dagger ket psi comma ket chi is nothing but complex conjugate of bra chi A dagger acting on ket psi. Obviously it means that bra chi A dagger ket psi complex conjugate must be equal to inner product of ket psi with A ket chi by definition. But in Dirac's notation, inner product of ket psi with A acting on ket chi is nothing but bra psi then followed by A operator acting on ket chi. So we have got a very beautiful result. So we will slide into the next page. I'll just take complex conjugate of both sides, and then we have got a very beautiful result which says the following object, bra chi acting on A dagger acting on ket psi is nothing but complex conjugate of bra psi acting on A acting on ket chi. Okay. Sometimes in some books, this is taken, those who do not use the bracket method of inner product, sometimes they define the joint of an operator by this equation 11. What we have shown is that starting from mathematicians' viewpoint of inner product, where they use the parenthesis, you can you can show the Dirac's way of also writing the fact that bra chi A dagger ket psi is equal to bra psi A ket chi complex conjugate. Okay. In some quantum mechanics books, it could be the definition of adjoint. But I've shown why flows from the definition of adjoint of an operator. Or class of operators which are extremely crucial for quantum mechanics. They are the self-adjoint or often called Hermitian operator. The word self-adjoint itself gives away what it means. It says that consider those linear operators which are adjoint of themselves. That's why self-adjoint. So therefore, a linear operator T is said to be Hermitian or equivalently. Actually, there are some differences which mathematicians talk about, but we will not, we physicists will take a cavalier attitude. So in this lecture, we will not distinguish between the mathematical nitty-gritties of self-adjoint and Hermitian. We will just take them to be Hermitian operators. So for quantum mechanics point of view, a linear operator T is said to be Hermitian if and only if its adjoint is itself, that is, adjoint of T is equal to T. All right. Now here, I must mention some things which Dr. Partho Goswami, when he was talking about operator acting in one direction and operator acting in another direction, essentially he was talking about this adjoint property. Okay, so Dr. Savita, can you go to the previous slide? Yeah, thank you, because a little bit, we can scroll down a little bit. Yeah, a little bit, no, we have to probably go up. The beginning of the definition of adjoint of an yeah. Let's. Dr. Partha Goswami at one point was saying that if you have an integral of some wave function, one operator acting on another wave function, you can think of this operator acting on the left-hand side. He was basically alluding to this equation number 9. After all, that joint definition is you have integral is associated with inner product. So it is nothing but you can think of inner product of ket psi with a operator acting on ket chi. But the definition of adjoint says, well, the adjoint of A can act on the first vector, and then you take the inner product with ket chi. So this is what Dr. Partho Goswami was referring to, and he used the statement that when you take matrices, then this becomes all right. What he was referring to it to was that, as we saw in yesterday's lecture, the bra can be thought of as a row vector, while ket can be thought of. So he was saying that that is what equation 9 is talking about. All right. So now let's go to the next page. Thank you. Yeah. So let's go down a little bit. Yeah. Right. So now we have defined what is a self-adjoint operator. So self-adjoint or Hermitian operator is simply an operator whose adjoint is the same operator. Now I'll again ask you to do an exercise. It's a very simple exercise. You might say that, okay, I have taken adjoint of an operator T and got another operator T dagger. What if I take once again the adjoint of T dagger itself? So I'm talking about general operators, not Hermitian operators. So please do this exercise. Show that if you take the adjoint of an operator A, then it will be A dagger. What if I take adjoint of A dagger? That will be A dagger, dagger. You can prove A dagger, dagger is nothing but equal to A. Okay? It's a very simple proof. So I urge all of you to do this exercise to show that dagger of A dagger is equal to A. This for all linear operator, not just Hermitian operators. Okay, let's come back to the Hermitian operators. So Hermitian operator is defined to be T dagger must be equal to T. Now, theorem A. This theorem, although it was proved by Dr. Partha Goswami, but in a wave function approach, I will do it in an abstract manner. By now, you have realized that our vectors, our operators, they are all abstract. What do I mean by abstract? That you cannot write down in terms of numbers. They are all at the level of symbol. While real numbers, complex numbers, they can be written down in terms of numbers. You can write a complex number as 3.3 plus iota square root of 5. But I can't write the ket psi in terms of numbers as it is. I can't write the operator T in terms of numbers. They're all abstract. So a linear operator is like, again, a machine where you provide an apple, the linear operator will give you an orange. Okay, it'll not return a coin. I talked about linear functional where you give a coin and it'll give you a can of juice. But linear operators are different. You give an apple to the linear operator will give you back orange. Okay, while this makes a nice analogy, but at the same time, the real linear operators are abstract, the real vectors are all abstract. What are not abstract are the eigenvalues. Okay, so first because they are complex numbers in general. So first theorem A, is to prove that eigenvalues of Hermitian operators are always real. The proof is very simple. Let's start proving it. So consider a Hermitian operator O. O stands for observable, because we'll soon talk about postulates of quantum mechanics and observables. So consider an observable or an operator which is Hermitian, and let lambda be any eigenvalue of this operator. So you have an equation that operator O acting on ket psi lambda is equal to lambda ket psi lambda. All right. Now soon what we will do is we will use a notation later where when you are talking about the eigenvalue lambda, why talk about a vector which is different? You might as well say, instead of writing psi lambda, you might as well say ket lambda. That symbol we will use later so that we don't have to say psi of subscript lambda. But anyway, let's go on with this. So imagine that you have a Hermitian operator O and its eigenvector ket psi lambda, such that when O acts on ket psi lambda, you get the eigenvalue lambda times ket psi lambda. All right. Now what I do is I take the inner product of this equation with ket psi lambda. In Dirac notation, there's nothing but bra psi lambda acting on O acting on ket psi lambda. After all, there's nothing but inner product of ket psi lambda of O acting on ket psi lambda. But I know that ket psi lambda is an eigenvector of O. So therefore, when O acts on ket psi lambda, it produces lambda ket psi lambda. So therefore, I get the equation that I get the inner product of ket psi lambda with O ket psi lambda is nothing but ket psi lambda, comma, the eigenvalue lambda, ket psi lambda. All right. But we know from the property of inner product that any scalar multiple acting on the rightmost vector, it'll just come out of the bracket. And therefore, we get the equation that indeed the inner product of ket psi lambda O acting on ket psi lambda is simply lambda into inner product of ket psi lambda with psi lambda. All right. So is this clear? So what we have proved is the inner product of ket psi lambda with O acting on ket psi lambda is simply lambda inner product ket psi lambda with itself. Now let's go to the next page. Yeah. So, okay, you have already gone there. Good. So we have the equation 12, which says bra psi lambda O ket psi lambda, which is nothing but inner product of ket psi lambda with O ket psi lambda, is simply lambda inner product of ket psi lambda with itself. Now what will we do? We'll use that result, the beautiful result which we proved, namely equation 11. If you refer to the equation 11, which said that bra psi O dagger ket chi is nothing but complex conjugate of bra chi O ket psi. But here, ket psi and ket chi are nothing but, they are identical, ket psi lambda. So therefore, if you use the result which we proved earlier, namely the equation 11, it tells us that bra psi lambda O dagger ket psi lambda is nothing but complex conjugate of bra psi lambda O psi lambda. This is a general result. But now bra psi lambda O ket psi lambda, we have already proved is nothing but lambda into inner product of ket psi lambda with ket psi lambda. Therefore, because I have taken a complex conjugate, it must be equal to lambda star complex conjugate of ket psi lambda with ket psi lambda. But we know complex conjugate of ket psi lambda with ket psi lambda is same as inner product ket psi lambda, ket psi lambda. Why? There's another property of inner product that we have done yesterday, which where the fourth property said, take any vector ket u, then inner product of ket u with ket u is always positive. Okay, is greater than or equal to 0, and in fact it is 0 only if ket u is 0. That is something we discussed yesterday, and therefore I don't have to take complex conjugate of the inner product ket psi lambda, ket psi lambda. We know complex conjugate of ket psi lambda itself is inner product of ket psi lambda, ket psi lambda. Only thing that gets the complex conjugation is the eigenvalue lambda. So what we have proved is, in general, bra psi lambda O dagger ket psi lambda is nothing but lambda star inner product of ket psi lambda with ket psi lambda. But now we are discussing about Hermitian operators. So O dagger is same as O, and hence this tells me that if O dagger is same as O, then we have proved that bra psi lambda O ket psi lambda is same as lambda star inner product of ket psi lambda and ket psi lambda. But compare now equation 12 and equation 13. Earlier we proved that bra psi lambda O ket psi lambda is lambda inner product of ket psi lambda with itself. But now we have shown that it is same as lambda star ket psi lambda and ket psi lambda. That means lambda star into this inner product of ket psi lambda with itself must be equal to lambda into inner product of ket psi lambda with ket psi lambda. But remember, ket psi lambda is an eigenvector. An eigenvector can never be zero vector. So ket psi lambda with ket psi lambda is a positive number. So positive number cancels both sides, and we have the equation lambda equal to lambda star. So this proves that indeed eigenvalues of any Hermitian operator is real. Now let us prove another important theorem, Theorem B, which says that eigenvectors of any Hermitian operator corresponding to distinct eigenvalues. So page please, where the main proof is there. Thank you. So imagine that you have a Hermitian operator. Let's call it again O hat. Remember that our operators, I am always okay. So consider O hat to be our Hermitian operator. And suppose you consider two eigenvalues, distinct eigenvalues, and corresponding eigenvectors. Any two distinct eigenvalues and the corresponding eigenvectors. So therefore, you have the equation the operator O acting on ket psi lambda 1 equal to lambda 1 ket psi lambda 1, and the operator acting on ket psi lambda 2 is equal to lambda 2 ket psi lambda 2. And we are assuming that they are distinct eigenvalues. That means lambda 1 is not equal to lambda 2. Okay. Now what I do? I take the first equation, namely O ket psi lambda 1 is equal to lambda ket psi lambda 1, and either I can say hit it with bra psi lambda 2, or I can say that take the inner product of the one. You are familiar with the Dirac notation. Any inner product can be either thought of as the bra acting on a ket. So what I do is take this equation O psi lambda 1 equal to lambda 1 ket psi lambda 1, and take the inner product of this equation with ket psi lambda 2. Then what do I get? I get, after all, O acting on ket psi lambda 1 is lambda 1 ket psi lambda 1. So therefore, I get the result that lambda 1 will come out of the inner product bracket. That is something we have become familiar by now from the properties of inner product. So therefore, we get the equation that inner product of ket psi lambda 2 with O acting on ket psi lambda 1 is simply lambda 1 multiplied by the inner product of ket psi lambda 2 with ket psi lambda 1. All right. But the left-hand side of the equation, I can use my definition of adjoint. So ket psi lambda 2 inner product O ket psi lambda 1, by definition of the adjoint, O dagger, the same as inner product of O dagger acting on ket psi lambda 2, comma ket psi lambda 1. All right. But again, we are talking about Hermitian operator. O dagger is same as O, but O acting on ket psi lambda 2 is nothing but lambda 2 ket psi lambda 2. After all, ket psi lambda 2 is the eigenvector of lambda 2. So therefore, that inner product of ket psi lambda 2 with O acting on ket psi lambda 1 is nothing but inner product of lambda 2 multiplied by ket psi lambda 2, comma ket psi lambda 1. Now, we will use the result of the earlier theorem. See, inner product property says that if I take out lambda 2, then it must become lambda 2 star. Remember the idea that in the first entry, inner product is antilinear, while in the second entry, the inner product is linear. So therefore, in general, if I take lambda 2 outside the inner product bracket, it should be lambda 2 star. Fine, lambda 2 star is all right. But we are talking about eigenvalues of Hermitian operators. Lambda 2 is real. So therefore, lambda 2 star is same as lambda 2 itself. So therefore, I get the result that inner product of ket psi lambda 2 with O acting on ket psi lambda 1 is same as lambda 2, inner product of ket psi lambda 2 with ket psi lambda 1. Now you compare. Now what you do, you subtract from equation 15, equation 14. If you subtract, what do you get? Oh, I made a typographical error, you see. This is why one has to be a little bit careful. It should be lambda 2 minus lambda 1. So if I subtract from equation 15, equation 14, that means from here, I subtract this. The right-hand sides are, left-hand sides are both same. So if I subtract from this, I'll get lambda 2 minus lambda 1. Please correct it. Here there's a typographical error. It's not lambda 2 minus lambda 2, but lambda 2 minus lambda 1. So I get, by subtracting from 15, 14, the result that lambda 2 minus lambda 1 multiplied by inner product of ket psi lambda 2 with ket psi lambda 1 is equal to 0. But we know that lambda 2 minus lambda 1 cannot be 0. But from our basic mathematics, we know if I have two numbers, product of two numbers is equal to 0, then one of them has to be equal to 0. So if lambda 2 minus lambda 1 is not 0, it means that inner product of ket psi lambda 2 with ket psi lambda 1 must be 0. This proves that eigenstates corresponding to distinct eigenvalues are mutually orthogonal. Okay, great. So let us summarize the results so far. What we have proved is take any self-adjoint operator, then all it's to be real. Not only that, all the eigenvectors corresponding to distinct eigenvalues, they'll be mutually orthogonal. Okay. What I will not prove is this. The result I'm going to only state is that in general, if you take a Hilbert space, oh, I have not defined Hilbert space, but I will define it soon. In general, if you take a Hilbert space and a Hermitian operator on that Hilbert space, then the set of all eigenvectors of this Hermitian operator forms an orthonormal basis. We have already shown orthogonality of eigenvectors corresponding to distinct eigenvalues. But if you have a set of orthogonal vectors by Gram-Schmidt procedure, which you are familiar with, you can make them orthonormal, or need not use, if you already have a mutual set of orthogonal vectors, you don't even have to use Gram-Schmidt. You just normalize each of the vectors. So I have already proved that for distinct eigenvalues, the eigenvectors are mutually orthogonal. What now I am stating without proof is that list all the eigenvectors of Hermitian operator. Of course, they will be mutually orthogonal, but I am now stating this can be proved, but I am not providing the proof, is that this list of all the orthogonal eigenvectors, they form a complete basis. That means any state vector can be written as a linear combination of these eigenvectors. And the orthonormal basis you can get by just normalizing each of the eigenvectors. They are, of course, orthogonal. You just have to normalize. Now let's come to postulates of quantum mechanics. So far, we have been only doing stuff that mathematicians had already done by the end of 19th century. Remember, all these things so far I discussed have already, are largely David Hilbert, Banach, they played important roles. All these mathematics was already done by mathematicians by 1900. Remember, quantum mechanics slowly emerged by 1920s, 1926 was Schrodinger equation, and so on. And it was the mathematician von Neumann, a genius mathematician as well as mathematical physicist, von Neumann, who came from Australia, not Australia, but Austria. So the Austrian mathematician cum physicist, von Neumann, he has contribution not only in physics, mathematics, but also on information theory, computers, and so on. It is he who essentially systematized quantum mechanics in this particular way. And Dirac also did a lot of the work on the formulation of quantum mechanics. Now let's look at the modern view of postulates of quantum theory. All right. And these postulates are not only true for quantum mechanics, but any theory which is quantum, whether it is quantum mechanics, whether it's quantum theory of electrons, or whether it's quantum theory of weakly interacting particles, strongly interacting particles, and so on, these postulates must be satisfied. All experiments so far, whether it is semiconductor physics, nanomaterial, high energy particle physics, gauge theories, um, take any theory, quantum electrodynamics, anything you see, they all have to satisfy all these postulates of quantum mechanics. So what is the first postulate? The first postulate states that if you take any physical system, for that physical system, corresponds a Hilbert space H. By the way, I have not yet defined Hilbert space H. So let me orally define. The actual mathematical definition of Hilbert space is very complicated, but we don't have to go into that nitty-gritty. For our purpose, we will define Hilbert space H as a linear vector space in which inner product is defined. It's a linear vector space over the field of complex numbers in which there is an inner product defined. And furthermore, the norm that is used is induced by the inner product. And we have already discussed how the inner product can norm of a vector. Mathematically minded, you might also add that this Hilbert space, all Cauchy sequences, take any Cauchy sequence, they will converge. But let's not go into this convergent Cauchy sequence and Banach space. They'll take us in a different route. So for our purpose, a Hilbert space is a linear vector space defined over complex numbers on which an inner product is defined, and this inner product induces the norm of a vector. All right. Second postulate. What is the second postulate? It says, fine, we have already said that every physical system, there corresponds Hilbert space. The second postulate says that for every physical state of the system, the physical state is completely represented by a vector ket psi which belongs to this Hilbert space. That means what? You cannot do anything better. A physical state of the system is completely specified by some ket psi belonging to the Hilbert space. That means there is no other information. Ket psi is the only information you can think of for the physical state of a system. Let's come to the next postulate. The next postulate says that take any physical quantity that can be measured. By now, we have been using the term observable for such things. So any physical quantity which can be measured in the laboratory, we are calling it observable because they can be observed. And the third postulate says that for every observable, there corresponds a Hermitian operator that is defined on this Hilbert space, script H. Okay. Now you see the importance of Hermitian operators. But we have to also talk about dynamics. After all, when you do classical mechanics, which equation determines the dynamics? Either you use Newtonian mechanics, or if there are constraints, you use Lagrange equation or Hamilton's equation, and so on. So they determine how the system evolves with time. In quantum mechanics, how does the physical state of a system evolve with time? We have already mentioned the physical state is represented by a vector in the Hilbert space, and the evolution is determined by this abstract Schrodinger equation, which says square root of -1, which is iota. So iota times h bar, remember, is h divided by 2 pi, multiplied by the derivative of ket psi t. So that I h bar time derivative of ket psi t is given by the Hamiltonian operator acting on ket psi t. And what is this Hamiltonian operator? Hamiltonian operator is also an observable. That means Hamiltonian operator is Hermitian. And what does it physically correspond to? The Hamiltonian operator corresponds to the energy of the system. Remember, The third postulate says every physical quantity that can be measured in the laboratory, it corresponds to a linear operator, which is Hermitian. So now you see how the worldview of quantum mechanics has gone to another level. Now, measurable quantities, they correspond to linear operators, which are Hermitian. And in particular, H hat is the Hamiltonian, which is an operator that represents energy of the system. Good. Now you say, okay, all these are so far fine, but when I make a measurement, what do I get? After all, science is all about measurement and also modeling how measurement and the time evolution of physical systems, how are they described? So time evolution of the state vector I have already showed, namely the Schrodinger equation. But what happens when I make a measurement? So suppose we have an observable, which is of course a Hermitian operator. Let's go to slide number 33. Right. So if you go to the slide number 33, then you find that the
Sir, we are on slide 33.
33 I've already got.
Yes, sir.
Yeah. Let me just view it in my system. What is slide number 33? Yeah. Yeah. So suppose you take an observable O, and by observable, that means it is associated with a Hermitian operator O hat, and you measure accurately that observable. And imagine that you have an apparatus that can measure this observable with extremely high precision. Then the postulate says that when you make a measurement, you will find one of the eigenvalues of the operator. By the way, here I must qualify. One of the eigenvalues is provided the operator O has discrete eigenvalues. When it is continuous eigenvalues, then of course you can ask, if I make a measurement, what is the probability that I get the value within a range? So at the moment, suppose the observable O has discrete eigenvalues. Discrete meaning what? Lambda 1, lambda 2, lambda 3, etc. While if it is continuous eigenvalue, it'll be parameterized by the real numbers, not parameterized by integers. So suppose the eigenvalues of O are discrete, meaning the eigenvalues are lambda 1, lambda 2, lambda 3, and there'll be infinite number of eigenvalues in general. Then the postulate says, if you make a measurement, then what you will get will be at random only one of the eigenvalues of the observable. That's all. You can't predict what eigenvalue you will get, but at random, you will only measure one of the eigenvalues. Of course, I am assuming that this measurement has been done with almost 100% accuracy. It's an idealization. By now, in physics, very often in the beginning, we do a lot of idealization. Of course, when we try to make contact with actual experiments, then of course we are more careful. We have to talk about measurement errors and so on. But at the moment, we are talking about principles, what principles are involved. So this postulate tells me that if I have an apparatus that with 100% accuracy can measure observable O, then upon a measurement, what I will get is one of the eigenvalues of the operator O. But can we say with what probability I'll get the eigenvalue? That then you have to go to the next postulate. The next postulate says that before the measurement, let's say the state of the system was evolving and the state is ket psi of t. So it is evolving, of course, on its own. On its own meaning, it has a Hamiltonian, and the Hamiltonian via the Schrodinger equation is telling how the state is changing with time. And we have performed a measurement, and let's say the observable O, its eigenvalues and eigenstates, eigenvalues are AI, I going from 1 to 3, etc. And the corresponding eigenstate, remember, I've already mentioned that we will now label the eigenstate by the eigenvalue itself. So the eigenstate is labeled by ket AI, meaning what? Eigenstate, of course, is an abstract vector. But the moment I say ket AI, immediately you know, okay, I mean that this is the eigenstate for which the eigenvalue, which is in our case a real number, eigenvalue is AI, which is a real number because it's a Hermitian operator. So we have an observable O and the eigenstates ket AI, so that when O acts on ket AI, I get the eigenvalue AI times ket AI. And we have at the moment we are assuming discrete eigenvalues. That's why eigenvalues A can be labeled by numbers 1, 2, 3, etc. I'll soon talk about also the continuous case. Now, the postulate says that if you make an accurate measurement at time t1, of course your outcome is AK, and AK eigenvalue will come with a probability. What is the probability? The probability is nothing but mod square of the inner product of ket AK with the state vector. Imagine the measurement is instantaneous. That means at T1 itself, you did the measurement. So at T1, before the measurement, the state of the system was ket psi T1. And this postulate says that you will find upon measurement the eigenvalue AK with the probability mod square of inner product of ket AK with ket psi T1. Remember, the inner product of ket AK with ket psi T1 is a complex number. To get the probability, you have to take the mod square. And this is the probability with which you will find the outcome of the measurement to be AK. Okay. And this is true for any observable, not just position, it's true for all observable. Now, you see the generalization I was talking about. So far, in the wave function approach, you knew that, well, if you have a wave function psi of r, if I measure position, then position measurement is associated with a probability density psi star r into psi, that is mod psi r whole square. But with wave function approach, it would be hard for you to figure out, if I make a measurement of the momentum, what will you get? You'll have to do additional work. Similarly, if you make a measurement of energy, what will be the probability and what will be the probability and the associated eigenvalue? You'll have to do much more complicated calculation. Here, it is general. It says that, well, if you know the state of the system ket psi of t, make measurement of any observable. And if you know the observable's eigenvalues and eigenkets, you can get the probability of finding a particular eigenvalue. Now we will make the correspondence of this for the case of position. Suppose, you say that, well, how do you know that this agrees with our knowledge of wave function and probability in the position measurement? Let's see. So now I'm going to do a correspondence to our wave function knowledge that you are very familiar with. So suppose you consider position as the observable. Remember, now we are talking from abstract viewpoint. So position observable, position in classical mechanics is just a vector with real components, x coordinate, y coordinate, z coordinate, but that is only a classical picture. Now we are talking about quantum mechanics where observables are operators. So my position observable R vector is now an operator. Of course, it has X component, it has Y component and Z component. So therefore, position observable is associated with three operators: X operator, Y operator, and Z operator. But for the simplicity, we can make a compact notation. We'll call R vector operator, which stands for X operator into unit vector I plus Y operator into unit vector J plus Z operator into unit vector K. All right. So now my R vector hat is a Hermitian operator, and it will have its eigenstates also. So consider the eigenstate ket R vector 0. Again, remember our notation that I will write the eigenstate and label it with the eigenvalue itself. So ket R0 is one eigenstate of the position operator R vector hat. That means what? When R vector hat acts on the eigenstate ket R0, you get the eigenvalue R0 multiplied by ket R0. Now, here I want to spend some time. Remember, the R vector operator is actually three operators: X hat, Y hat, Z hat. So this equation must be read as three different equations. And what is the equation? X operator acting on R0 ket will give you X0 into R0 ket. Y hat, which is the Y coordinate R0, will give you 0. And Z hat operator acting on ket R0 is Z0 ket R0. Okay. Now, let's go back to that theorem I stated, but I did not prove. Namely, in a Hilbert space, any observable, if you list all the eigenvectors, this eigenvector, the list of eigenvectors forms an orthonormal basis. So let's go to my last slide. Yeah. And since the position operator R vector hat is a self-adjoint operator, that means X hat dagger is X hat, Y hat dagger is Y hat, Z hat dagger is Z hat. This is an assumption because after all, it is an observable and we can measure position. And whenever we make measurement of position, we get real numbers. So therefore, the operator representing the position observable must be a self-adjoint operator. And its eigenstates, I have again made a typo. The so-called orthonormal basis, the set is not the eigenvalues are, but it's ket R. So I have forgotten this ket R. So please correct it. Here in the second line, it is a set of eigenkets ket R, not eigenvalues. By now, the notation must be clear. R vector are the eigenvalues. This is X, Y, Z, the three real numbers. That is what is R vector. They are the eigenvalues. But the eigenstates are ket R. So I missed out on the ket symbol. So make this notation change. The orthonormal basis is nothing but set of all ket R. Remember, the eigenvalues are continuous. They are not discrete. Okay, so although in the previous example, when I was talking about the postulates, I assumed discrete eigenvalues. Now we have come to position. We know that position in whatever we know so far, position measurement, the position and orthonormal. There, when I talked about orthonormal basis, I said that orthonormal basis vector, if they are ket v1, ket v2, ket v3, etc., up to ket vn, the orthonormality condition is inner product of ket vi with ket vj is delta ij. That means bra ket vi acting on ket vj is Kronecker delta ij. But that was because the eigenvectors were part of discrete eigenvalues. So when you have continuous eigenvalues, the Kronecker delta gets generalized to the Dirac delta. As you know, Dirac delta is not a function, it's a distribution. And I'm sure in many of your tutorials, in fact, Dr. Sukant Datta in the previous lecture was talking about Dirac delta properties of Dirac delta, etc. And I'm sure you will do a lot of exercise on Dirac delta function. So in our case, when you have continuous eigenvalues, remember, what are the continuous eigenvalues? Three sets of eigenvalues: x eigenvalues, y eigenvalues, z eigenvalue. Therefore, in our case, the orthonormality condition is not the Kronecker delta ij, rather the inner product of ket r with ket r prime, which in Dirac notation is bra r acting on ket r prime, is delta cube r minus r prime. What do I mean by delta cube? Remember, r has three components, x, y, z. R prime has three components, x prime, y prime, z prime. What delta cube r minus r prime represents is product of three delta function. It is delta cube r minus r prime is delta of x minus x prime multiplied by delta of y minus y prime multiplied by delta of z minus z prime. Okay. So delta cube r minus r prime is a short and compact form of the product of three delta function, delta x minus x prime into delta y minus y prime into delta z minus z prime. Again, I have made the same typo. This statement as R constitutes a basis, orthonormal basis, is not curly bracket R curly bracket N, but ket R. So please make that correction. So since the set of all ket R's constitutes an orthonormal basis, therefore any state vector can be written as a linear combination of basis vectors. Normally, if you have discrete basis vectors, ket v1, ket v2, ket v3 up to ket vn, any vector ket psi can be written as alpha 1, ket psi 1 plus alpha 2, ket psi 2 plus so on up to plus alpha n, ket psi n. But now you see ket r is not discrete. For every value of r, there is a ket, it's continuous. So therefore, the summation will become integral. And here, there are three quantities, x, y, z. So therefore, it will be a triple integral. So any arbitrary state vector ket psi, because my ket r, collection of ket r forms an orthonormal basis, I should be able to expand ket psi as integral of the coefficient of expansion psi of r prime into ket r prime integrated over d cube r prime. This is the generalization of summation, because in our case, we have, in the case of position, we have continuous eigenvalues. So we have the eigenvalues forming a continuum, and therefore instead of summation, we will have integral. So as the collection of all ket r forms an orthonormal basis, any state vector ket psi can be expanded as integral psi of r prime, which is a complex function, psi of r prime, multiplied by ket r prime into d cube r prime integrated over all r prime. Okay, good. But now you will say that this is nothing but an abstract ket psi, which has been expressed as an integral of some complex function psi of r prime, okay, into ket r prime integrated over d cube r. prime. So both ket psi and ket r prime, they are all abstract. They cannot be written down in numbers. But well, why have we got a facility like inner product? To get them written in the form of numbers, let's use inner product. So let me hit bra r to ket psi in this equation. Hitting bra r with ket psi is same as taking inner product of ket psi with ket r. By now, you are familiar with the Dirac notation. So then the equation is bra r acting on ket psi, and remember, bra r is a linear functional. If it's a linear functional, it will go through the integral. Remember the linear properties of the bra vector that I talked about yesterday. So bra r will go through the integral. After all, what is an integral? Integral is nothing but infinite sums, right? So therefore, bra r will go through the integral. It'll go through the complex function psi of r and directly hit ket r prime. Okay. So therefore, what have we got? We have got bra r hitting on ket psi equals integral complex function psi of r, bra r hitting ket r prime. But we know the orthonormality condition says that bra r ket r prime is nothing but delta cube r minus r prime d cube r prime. And by now you know what to do with a distribution like delta function. Delta functions, remember, they are all defined only within integrals. And by now you know how to integrate some function multiplied by delta function. So integral psi of r prime delta cube r minus r prime d cube r prime is nothing but psi of r, using the very definition of delta function. What is the very definition of delta function? Take delta of k minus k naught. What is the definition of delta k minus k naught? This is the only definition of Dirac delta. That is, delta k minus k naught is such an animal that if you multiply delta k minus k naught to a function f of k and integrate over k, then what you will get is f of k naught. That means f of k naught is equal to integral f of k into delta k minus k naught dk. This is the definition of delta function. There is no other definition of delta function, where f of k, of course, for this definition to work, f of k must be a function that goes to 0 at k tending to infinity and k tending to minus infinity. These are called test functions. So please read up about Dirac delta function in more details, because Dirac delta function, by the way, this was also another great innovation by Dirac. He used it, and mathematicians that time, when they saw the use of Dirac delta, they said, what is this? This is not a function. How can you think of a spike infinity at a given point? Then the mathematician developed a whole theory called distribution theory to explain the Dirac delta function. So you see, Dirac's mathematical imagination was something which was astounding. You just pull up something from his abstract mathematical thinking, and which will become very useful in physics. So please study Dirac delta function in detail. Not only they are useful in quantum mechanics, they are useful in all of physics, whether electromagnetic theory, Green's function technique, or in signal processing, those who want to do gravitational wave data analysis, match filtering technique to pull out weak signals from noise. All these require a very good knowledge of Dirac delta function. All right. So using the Dirac delta function, what have we achieved? We have achieved the result that inner product of ket r with ket psi is nothing but psi of r. And psi of r is the wave function. So what I've showed you is the conventional wave function psi of r, which was how you started learning quantum mechanics is nothing but inner product of the eigenstate of the position operator with the abstract state vector ket psi. Now, you can immediately generalize this to all other observables. So the same thing I can generalize to momentum. I can say that, well, ket psi is the actual state, is the abstract state describing the physical system. If I want to know what is the probability, here, for example, the probability part immediately comes through. If you ask, what is the probability density of finding the particle at position R? Go back to the postulate. The postulate says you have to take the inner product of the eigenstate with the state and mod square. Here it is nothing but bra R acting on ket psi, which is psi of R mod square, and you have got back your probability density mod psi R square from the postulate itself. But now that we have got a general formalism, I can do it for any observable. Supposing I was not interested in position observable, I was interested in momentum observable, then I can ask the same question. Well, momentum operator again is an abstract operator whose eigenstates ket p form a orthonormal basis. And again, I will do the same thing. I'll say that what is uh, bra p acting on ket psi? Bra p acting on ket psi will be the momentum space wave function psi tilde of p, and the probability density of my finding the momentum value p is nothing but mod psi of p whole square. That will be the probability density. Density because momentum is also a continuous variable. All right. I will stop here. I will answer the other question. So I have answered one question. That is, I had posed it long time back, namely, how do I calculate the probability or probability density for any observable? With the abstract formalism, the answer is clear. All you have to do is take ket psi, take the inner product with the eigenvector of that observable, and you will get the probability amplitude for measuring that eigenvalue. For mod square, you'll get the probability. So this is the general procedure. But I have not yet told you why should in the position representation, why should the momentum operator be minus IH bar gradient operator? Okay. I will not derive it fully in the next lecture, which is going to be on Sunday at 6 o'clock. I'll give you a hint because it relies on a lot of Dirac delta function procedure, and it will take away certain time. I will only give it to you as a problem. But I must tell you before I stop, the real reason why this happens is from the commutation relation. I have not yet introduced the commutator bracket. Two operators, A and B, their commutator bracket written as square bracket A comma B square bracket N is defined to be A operator then followed by B operator minus B operator followed by A operator. So commutator of two observables or any two linear operator A and B is nothing but AB minus BA. And by now you know that in general operators, they don't commute. In general, AB is not equal to BA, unlike numbers. How do you know this? You have already known this from matrices. Product of two matrices in general are not commutative. Okay. So therefore, matrices correspond to operators given a basis. That also I will show you in the lecture on Sunday. So the commutator bracket is what tells us how position and momentum operators must be related. Although I will not show you in detail the result, but I'll just tell you the following result. The abstract position operator, let's say the x component of the position operator x hat, and the abstract x component momentum operator p hat, they are such that commutator of x with px is equal to iota into h bar into identity operator. It is this which tells us many things. It tells us why there is uncertainty in simultaneous measurement of x and px, why the momentum eigenfunctions are plane wave, why in the position representation momentum operator can be written as minus I h bar, that is px can be written as minus I h bar del by del x. They all follow from the commutator bracket which says x hat comma p x commutator is equal to, which is nothing but x operator followed by px operator minus px operator followed by x operator, and it is equal to iota times h bar into the identity operator. So the abstract formalism gives a unified picture of why is it that momentum wave function uh, is related to the Fourier transform of the position wave function. Why is it that eigenfunction of position is e raised to power ip dot r by h bar? After all, that is what relates the de Broglie wavelength of a particles having a momentum p. They all follow from the commutator bracket. It's a, I mean, to do justice to whatever I have said now, it'll take 3 or 4 more lectures, but I will only list down the results on Sunday's lecture because some of the basic things must be done in detail. These results, which normally we do in the MSc quantum mechanics lectures, I will only state the result. Those who are interested, you can look at books written by Professor Joy Ghatak, books by Sakurai's Modern Quantum Mechanics, R. Shankar's Introduction or Principles of Quantum Mechanics, Dirac's Principle of Quantum Mechanics, Matthews and Venkatesan. There are many good books on quantum mechanics. So I'll stop here and I will be very happy if you ask me questions. Dr. Savita, are there questions?
Sir, I'm looking for the questions in the chat box.
Okay.
Sir, on Zoom, there are no questions. Now I'm checking the YouTube. Or
All right. Okay.
sir, I think there are no questions.
Yeah, I think it has become too mathematical and heavy. Students have been already following too many mathematical subjects. They are probably tired by now.
Yes,
Yeah.
sir, maybe. I again request students, if you have any question, you can write it in chat box right now, or otherwise we are going to end this session. I think, sir, let's end the meeting.
All right. Okay.
Uh,
So,
okay. So,
those students who have remained, those who are still around, my advice is take some good books and do the derivation and do some problems so that you get a good hold of this abstract formalism that is so relevant for quantum mechanics.
I think, sir, there is one question by
Okay.
Vara Lakshmi.
Okay.
She's
Yeah.
asking how to define the exact definition on microstate and macrostate in quantum mechanics.
Well, microstate and macrostate, they are related by the direct product of Hilbert space, which I have not covered. Yeah, it's a very good question. Let me explain it. Supposing you have a single particle. The single particle with 1 degree of freedom will have one Hilbert space associated with it. Suppose now you take another particle, then the Hilbert space which describes these two particles will be the direct product of two Hilbert spaces. Let's say there's a particle 1 and particle 2. For the combined system will be H. What does it mean? Do I mean by a direct product Hilbert space? That means the state of the combined system 1 and 2 will be nothing but linear combination of products of individual states. That means a general state describing the two particles will be of the form alpha ij into ket psi into ket psi I into ket phi j, where ket psi I describe particle 1, ket phi j describe particle 2, and the general state of this combined system 1 and 2 will be linear combination, that is summation over I and j, alpha ij, ket psi I into ket phi j. See, for two particles itself, you can see the entangled, which is complex. If you add more and more particles, so there are n particles, then there'll be a direct product, H1, direct product H2, direct product H3 up to Hn. And you can see the complex entangled state that describes a collection of such a macroscopic system, n particle system. All right. So many body quantum mechanical system therefore becomes very complex because it involves direct product of many states. And there are very nice techniques like Fock space technique, Fock space states to describe such many body systems. So when you do solid state physics, where you have a macroscopic system with many electrons, then you use the Fock space idea, which is basically you quantize and talk about many particles in terms of such direct product states. Have I answered the question?
yes, sir. Sir, there is another question. I think this is the last one.
All right.
Someone is asking, in Hilbert space, eigenvalues are discrete or continuous?
It depends upon the observable. So there are self-adjoint or Hermitian operators whose eigenvalues are continuous, just like I said, position operator R, or momentum operator minus I h bar gradient operator. As you can see, their eigenvalues are continuous. They can take any value. On the other hand, if you take a bound state, like let's take the Hamiltonian corresponding to the hydrogen atom. We have solved this many, many times, and we know that the eigenvalues are discrete. We know that En is proportional to minus 1 over n square, where n is the principal quantum number, and n goes from 1 to, and it can go to infinity. So eigenvalues of Hamiltonian operator for hydrogen atom clearly gives you discrete eigenvalues. Similarly, the angular momentum operator, whether you take orbital angular momentum L square or spin angular momentum S square, the eigenvalues of angular momentum always is discrete. So for example, you would have proved while doing hydrogen atom problem that the eigenvalues of L square is L into L plus into square of H bar, where L goes from 0, 1 to etc. So clearly, eigenvalues of L square is discrete. It is L into L plus 1 H bar square. The eigenvalue of Lz is also discrete. It is M into H bar, where M goes from minus L plus 1, minus L plus 2 up to L minus 1 into L. So similarly, the half integral spin electron, as you know, is having half integral spin. So does proton or neutron. For spin half particle, the eigenvalues for Sz are 2. Either it will be minus half H bar or plus half H bar. So angular momentum, the eigenvalues are always discrete. So ultimately, it depends upon the observable that you're interested in. The continuous eigenvalues or discrete eigenvalues depend on the observables that you're talking about. All right?
Okay, sir, there is one more question by Akita.
Sure.
He's asking, does the Hilbert space also evolve with the evolution of state? Or does it remains the same? That is, we consider the Hamilton maps the space to itself.
Correct. So the second is right. So Hilbert space is the set of all state vectors. All right. So by definition, it contains all the state. It is a state vector which changes with time. So your Hilbert space is a collection of all state vectors possible. And Schrodinger equation tells you start with some ket psi t0, it'll move over to ket psi t1, it'll move over to ket psi t2, of course, continuously. So the state vector will keep on changing. So in other words, as you correctly said, the Schrodinger equation maps the Hilbert space to itself.
Okay, I think that's all, sir. There are no more questions.
Great.
Okay, sir. Thank you. Thank you for such a fast-paced talk. Thank you so much.
You're welcome, Dr. Bindal.
It was indeed a pleasure. Thank you. And I think now we'll be again listening to you on Sunday.
Yeah. So Sunday at 6 o'clock, right?
Yes, sir. 6 today. So,
yeah. Thank you.
Thank you, sir. Thank you so much. So, Dr. Savita, I think we can stop the recording now.
Yes, ma'am. Thank you very much, sir. Thank you, ma'am.
Thank you. Thank you, Dr. Savita. Thank you, Dr. Bindal. So have a good night.